Okay, so just so you guys know, here is today's lesson on periodic trends. And whenever I teach you guys live, it actually live streams. So if you were sick or away and desperately want to follow along with chemistry, you can actually click and follow along the course kind of live as we go. But then that link becomes live afterwards and you can see the lesson after the fact. So you can always rewatch lessons. All right. Oh, for goodness sakes. There we go. Okay. Okay. All right, here we go. So what I want to talk about today is what the periodic table tells us. So we've spent a little bit of time talking about how the periodic table is developed, right? You guys saw a lesson on that on Friday. Was that Friday? A day. And he was right. So we talked about the various experiments and the various scientists who led to our understanding of how the periodic table works, right? Do you remember a bit of that? Right, so de Bernoulli's triads. If you took certain groups of 3 and average mass, and so he thought those were groups. And sort of as time went on and on and on, we developed this model of the periodic table. Who's the guy who finally put it together? Yeah. Oh, sure. So again, today's assignment is under 1.5 assignment on the OneNote.
What's due today? I'm still lost as to what's due when.
Okay, so officially the assignment I gave you last week is due today.
The practice, all that practice you just did. Like
That wasn't due. Like that's not an assignment. That was
what people think you asked for.
No, okay, that was homework. Though you should do your homework. But that was just homework. That's just learning how to do the stuff. Due today, due by tomorrow is a new assignment for today. It's on the same topic. It's a bit more complicated. It's online. People will probably need a bit of help with it. I'm around all day to be found.
Is that like today's work?
Yeah, so if you go on OneNote, it'll say 1.5. Oh boy, losing the voice. 1.5 assignment under today's date. Can you let people know that?
And then the 1.8 is
1.8 is due before the unit's done. The sooner you get it to me, the sooner I can get back to you.
okay.
You're welcome. I'm seeing a real difference in the effort level from my 4Us who are actually in grade 12, and then this group, who like 2 people did their homework, and I'm just going to bury them on this test on Friday. I'm just going to happily fail a lot of them. And then they can learn that if you don't do your homework, you don't pass. 4U level course. Hi, what can I do for you?
I've got a question.
Sure.
Do you mean like for the 1A, it's got the identify type of bonds?
Yep.
Do you mean like the
Sigma or pi.
bond? Okay.
Yeah, sigma or pi.
Just making sure.
Yeah, anytime I ask type of bond, we're talking sigma or pi. Okay, so today we're going to build on, by the way, what was his name again? Anyone?
There's 3.
Yeah, the final one, the guy who really put it all together and sort of is the foundation of our Mendeleev. That's right. Looks like Mendeleev, doesn't it? But Mendeleev is the guy who gives us our modern periodic table. And the amazing thing we mentioned was that he did what? He started putting these things onto a table and organizing them. Yeah, which is amazing, right? And talk about a validation of a theory, where he said, here's something we haven't discovered yet, but I'm confident we will find it. And when we do, it should be a metal, and it should weigh something like this. It should be dense. It should be reactive like this. Made all these predictions about these things that we didn't even know existed yet. And he was right. And he was right because his theory fit the facts, which is really what science is about, right? It's about making predictions and adjusting your predictions. But again, it's a mistake to think that Mendeleev comes out of thin air, right? And just says, oh, hey, we could do this. And that's why we go through that lesson. And we sort of show you in steps where this thing came from. So today, I want to talk about a few things. So having learned about how atoms are arranged on the periodic table, we'll now discuss what the modern periodic table tells us about atoms. Okay. So Niels Bohr developed a model of the atom in which the protons and neutrons form a massive nucleus at the center, and electrons orbit around the nucleus in specific shells. right? And this is the one you learned in grade 9, right? You drew all those diagrams where you put the letter in the center and draw the electrons around. All right, and then you did that again in grade 10. All right, and each shell holds a fixed number of orbitals, or a fixed number of electrons, rather. Do you remember what that is? How many electrons fit in the first shell? Good, what about the second shell?
8.
Great, what about after that?
8.
Yeah, it gets confusing, but we say 8.
Oh.
It's a bit of a lie, but it's what we taught you. So you're repeating it correctly.
Oh wait,
What can I do for you?
We just have a quick question.
Yep.
You're asking if it's bonding in potassium bromide. Do you
Yep.
mean like ionic or covalent, or do you mean like stuff like?
I mean ionic or covalent.
Okay.
And then if it's covalent, tell me specifically sigma bonds or pi bonds.
Okay.
But for example, you know that one will probably work out to be metal and non-metal. I mean, likely it's going to be good.
I don't know, but inside our discussion, do you guys say 16 about something or no?
18 actually.
18?
But again, don't worry about it. But yeah, the idea is that each shell of electrons holds a specific number. All right, for the purpose of this course, you can think of it as being 2, 8, 8, and then 18. All right, and so if we were to draw a Bohr-Rutherford diagram of sodium, you remember we'd put the number of protons and neutrons in it. Where do those numbers come from, 11 and 12? You don't need to worry about drawing the periodic table entry. How did I get 11 protons, 12 neutrons? Good. So the atomic number tells me the number of protons. Good. And the atomic mass tells me the number of? No. What does the mass number tell me? Yeah, how much both are together. And so if we subtract, we can figure out the number of neutrons, right? So if the whole thing has to weigh 23, and 11 of those are protons, we subtract, and 23 minus 11 gives us 12. Good, so that's how many neutrons. And then when we draw the electrons in, how many electrons does sodium have to have total? Good, why 11?
The same amount of protons.
That's right, because overall the whole thing has no charge, right? So how many will go in the first shell? 2, leaving me with how many left? Good. How many go in the second shell?
3.
Good. 1, 2, 3, 4, 5, 6, 7, 8. Leaving me with how many?
1.
Great. And where does it go?
On the third.
In the third shell. That's right. Yep.
Is there a specific way that you have to place the electron?
Yeah, and in fact, I haven't done it well. So as a rule, we actually do it like this, where we put them in pairs. So normally we would actually do it like that. So I haven't drawn it ideally. All right. Now, a diagram like that can help us to visualize some of the trends in the periodic table that we're going to talk about. All right. And so I want to talk about a few different things today. And the first thing is just a reminder of what we call things. So the horizontal rows on the periodic table are called periods. All right. And I want to make a note about that. In the first row, and I don't have a periodic table in here, but which 2 elements are in the first row? Does anyone remember? And? Nope. Can you think far on the other side? Good, helium. And if you think, those have electrons only in which shell? First shell, right? Because hydrogen has 1 electron, helium has 2. As soon as we get to the second period, all of a sudden we're on to the second shell. By the way, how many atoms are in that second period? How many electrons does the second shell hold? 8. And if you look, that second period has 8 different elements in it, because the first one has 1 electron in its outer shell, then 2, then 3, then 4. But everything in that second period has 2 shells. When we get down to the third period, we are now in the third shell. So the period tells you the number of shells. Did you guys know that before? I'm always curious to know what people do and don't come in with. I don't think I knew that until I was like 26. Long after I should have. Okay, what do we call the columns? Groups, or sometimes you'll hear families. That's right, good. So the vertical columns are called groups or families. What do they tell you? Everything in group 1 has what in common?
Electrons and shells of valence shell.
Good. Wow. All right. It tells you the number of electrons in the valence shell. Yep.
What's the
Sorry, number of electrons. I read that a lot for electron. Sorry, have I not?
Oh, that's
see.
an of?
Oh, that's an of. Yes, I'm
That's like
sorry.
a fancy symbol.
Is that better?
Yeah.
Great. I am messy today. I'll try to be neater. All right. The older system used to have them 1 through 8 and the letters A and B. Now, a modern product table, I remember the families of groups, you know? Numbers up top. I'm taking a good look. That's okay. We just number them 1 to 18. But you'll still see periodic tables that have 1A, 2, like 3A and 3B. I actually like the old system better, but we've kind of done away with it. It's not what you see so much anymore. Okay, all of that is just preamble to what we're actually talking about today. I did make a little note about major families that you probably learned about in grade 10, right? The noble gases, what are they? Noble gases.
Argon, krypton.
Xenon and radon, yep.
Yeah,
What can you tell me about them?
they form
What do we know about them?
diatomic.
No? Where are they on the periodic table? All these guys. I'll give you a hint. What?
In the second half,
Yeah, specifically, what row are they?
the last one.
Very good, the last row. Which means what? If it tells us how many electrons they have in their outer shell, what's true about all of these outer shells? Yeah, so the last group on the periodic table, they have a full outer shell, which means that they are stable, they're full, they're happy. Do these things react? Let me ask you this. If you go to a football game and you see like the Goodyear blimp going overhead, if you'd seen that in 1920, it would have been full of hydrogen. Today it's full of helium. They used to use hydrogen because it's the lightest atom. Now we use helium. Why? Yeah, hydrogen reacts. It explodes. You've heard of the Hindenburg, presumably? Right? Famous airship that exploded and burned on the ground. Helium, even though it's a little heavier, so it doesn't do as good a job as hydrogen, helium's a noble gas, which means it has a full outer shell. It doesn't react. Now let's compare that to the group 1. Lithium, sodium, potassium, rubidium, cesium, francium. What do you know about them? Surely in grade 9 or 10, somebody dropped one of these into a bit of water for you. Did that happen? Yeah, what did you see?
It exploded.
It exploded.
Yeah, it exploded.
Yeah, if you put helium in water, would it explode? No. Why do lithium, sodium, potassium, rubidium, cesium, and francium explode when you put them in the water? Yeah. And in fact, not only do they not have a full shell, but how many electrons do they have? 1. So it's really easy for them to get rid of that, right? So if the goal is to get a full shell, you can try to gain them, or you can get rid of electrons, right? Well, for lithium, sodium, potassium, rubidium, cesium, and francium, getting rid of that last electron is super easy because there's just one of them. And so they're very, very reactive. Whereas if you look at group 2, these all have 2 electrons in their outer shell. And so they are reactive, but not as much. Magnesium does not explode when you put it in water. This is made of magnesium, right? If this were made of lithium, I'd have a problem. My hands are sweaty right now. I'd be catching fire, which would be bad. If I ever told, I guess I've never taught you guys. I had an unfortunate incident where I had a janitor mopping up a room I'd taught at Grimsby, and without realizing it, when I had done the sodium reaction, it had splattered sodium various places, and not enough to do anything dangerous, but still, as this poor guy was mopping the floor, every time he hit a speck of this thing, it would go and go up into flames. So can you imagine being this janitor who's just been doing your job, and as he's doing his job with, they have that power mop wheelie, and he's going around and it's just catching fire over and over again. So I got a nasty email.
Awesome.
Yeah, I got a nasty email about that, and a well-deserved nasty email. Anyway.
I don't know. I think that's kind of cool.
So did I. Anyway, so today we're going to talk about trends on the periodic table. And we're going to talk about a few things. Atomic size, how big are atoms, is one thing we're going to talk about. Then we're going to talk about ionization energy, electronegativity, and electron affinity, and I'm going to tell you what each of those things means. All right, so 4 trends we're going to talk about today. The first one's atomic radius. When I say radius, what do I mean? The radius of something. Yeah, the measure, we imagine that an atom is basically a sphere. It's the measure from the center of that sphere out to the edge. All right, so the size of an atom is typically measured as the radius from the center of the nucleus to the outermost electron shell. Now, let me ask you this. As we add more and more shells, what's going to happen to the size of this thing? Yeah, does that make sense? As we put more shells on the atom gets bigger. That's pretty straightforward, yeah? Which means that as we move down the periodic table, what should happen? Remember, we said every time we move down a row, we're talking about being in a new shell, right? So as we go down the periodic table, what happens to the size of these? Don't look at the picture.
They're going to get bigger.
Yeah, they're going to get bigger because we're adding more shells, right? So the trend is that atomic radius increases as we go down the table. Logical, right? The next one might not be as logical. Look at the picture, since you're doing that anyway. What happens as we go left to right? Explain that. Why would they get smaller? Because as we go left to right, we're adding more electrons, right? So shouldn't adding more electrons make it bigger? Right? Like if we stood on the left side of the periodic table, and in the same row we start going right, we're putting more and more electrons in. So we should expect it to get bigger, should we not? But look at the picture. What happens? It gets smaller. Any ideas? Well, first things first, all those electrons are going into the same shell. So even though we are adding electrons, it's still one shell. So should the shell get any bigger? No. So that explains why it doesn't get bigger. Now about why it gets smaller. As we're adding electrons to the orbitals, what are we also adding as we go across the periodic table? What else changes about an atom?
Just gas, neutron.
Neutron, sure. What else? Yep, the weight increases. What else? Protons, good. We add protons, we add neutrons, it gets heavier. So as the nucleus gets heavier, because of the neutrons and the protons, and it gets more and more positive, well, if the nucleus is positive and the electrons are negative, they're attracted to each other, right? Well, if the positive charge in the middle gets bigger, what's going to be true about those electrons? Not smaller, but they're going to be more attracted to the nucleus, right? If we have more and more positive charge in the nucleus, those electrons are more and more attracted to it. And that means that they're going to pull in closer and closer. And what's that going to do to the radius? It's going to make it smaller. So for atoms with the same number of electron shells, elements in the same period, the atom with more protons in the nucleus will be smaller because the electrons are attracted to the positively charged nucleus. Proton in the nucleus. Ooh, that's what happens when Joe has 2 coffees. It's all jitters and energy.
Oh, are you?
Yeah, it's great.
Sorry.
No, it's a win.
Oh. We'll ask them.
Gonna see me through. Well, I don't think they're too happy with me today, but I'm not too happy with them, so it's a fair trade.
I'm rather indifferent.
The trend is that atomic radius gets smaller as we go left to right. All right, now this is key because if you really understand how radius works, the next two will make sense. So as we move down the periodic table, what happens to atoms? They get bigger. As we move up the periodic table, then they get smaller. Good. As we go left to right, they get smaller. So if we go right to left, they get bigger. Okay. That trend is important. And understanding why. All right. As we go down, they get bigger because we're adding more shells. That one's really straightforward, right? You know? But then the other one is a bit more complicated. But as we move left to right, they get smaller because, you know, you've been teaching too long when your natural inclination is to go, it's when you move left to right, which to you is left to right and to me is right to left. But I discovered that in my own life, is that now when I'm talking to people, I say, you know, so going left to right. Anyway, that's just my little observation.
Because they're all going.
Yeah, this guy's an idiot. I can't believe he teaches. They get smaller because the nucleus has more protons, and those protons pull the electrons in. All right, and there's the diagram I gave you. Yeah? Okay. Now the next one's called ionization energy. What's an ion? What's an ion? That's an ionic bond. Sure. Even more simply though, what's an ion? Do you know? It's when an atom does what? A single atom becomes an ion two ways. It can gain an electron, and if it gains an electron, if it gets more electrons, what kind of charge will it have? Good. Or it can lose electrons. And if it loses electrons, if it gives them away, what will its charge become? Positive. Good. So that's how we become an ion. Now, ionization energy, what's that mean?
Your energy formed when you lose the gas.
Yeah, that's good. That's it. The ionization energy of an atom is how much energy it takes to take an electron away. Now, just to be clear, that's only one of the two ways of becoming an ion, right? But specifically, ionization energy has to do with just the one. It's how much energy it takes to take an electron away. All right. Now, let's talk about this. If an electron is far away from the nucleus has that positive charge, right, that pulls the electrons in. If an electron is really far away from the nucleus, should it be relatively easy to take away or hard? Easy, right? If I were trying to steal Miss Smith's computer, is it going to be easier for me to do if she's halfway across the room or if it's right next to her? Yeah, right? I was thinking of an
easier this one or this one.
I was thinking of an analogy, and the most immediate one was like kidnapping children. And I thought, well, that's dark. That's not a good analogy at all. So then stealing Smith's computer seemed less dark. Yeah, no, nothing dark.
I'll take it.
Oh, I know. Yeah, no, it'd have to be far. I'm quick though. Jeez, speaking of dark.
Just happens, yeah.
That's because, I mean, there is a hammer right there. All right, fair enough. So the same is true with electrons, all right? Electrons way far away from the nucleus are easy to remove. But electrons really close to the nucleus are hard to remove. So think of it this way. If an atom is big, its electrons should be farther away, so they should be
Easier to take away.
good, easier to take away, which means it should take less energy, right? So if an atom is big, the energy required to make it an ion should be pretty low. Whereas if an atom's really small, the amount of energy required to make it an ion should be pretty high. Does that make sense? Think then, what should be the hardest atom on the periodic table to make an ion? Yeah, a noble gas, specifically helium, right? Because helium is in the first shell, so it's only got one shell, and that's all the way to the right. So it should have this tiny little orbital shell. And that's true. Helium has the highest ionization energy. Whereas if we go the other way, if we go to the bottom left, francium, it has the lowest ionization energy. It doesn't take much energy to make it lose its electron. We know that because francium is so low that just being put in water, that water has enough energy to make it ionize, and it does it really quickly and it explodes, right? Really low ionization energy. So the trend is that ionization energy decreases as you move down the periodic table. And then remember that we said that in a row, as you go to the right, atoms have more protons, giving more pull on the electrons. So as we go across the periodic table to the right, the pull on electrons from its own nucleus gets stronger and stronger. So it should get harder and harder to steal those away, right? So as we go across the periodic table, the ionization energy goes up. Howdy. In other words, what you'll notice is that it is the exact opposite trend to radius, right? When radius is getting bigger, the ionization energy is getting smaller. And when the radius is getting bigger, because it's hard to steal electrons from a full one. And there's a formula for this. So this diagram you have, this diagram you also have. And look, what's the highest one? Helium. The lowest ones, lithium, sodium, potassium, rubidium, cesium, all of those highly reactive ones, right? And, oh gosh, oh goodness only knows what I just did. Okay. What? Okay, no, I don't want, I just want, there we go, okay. And, oh, and there's a formula for this, which is that the ionization energy works this way. If we start with an atom, and we add ionization energy, we said it's the energy required to make what happen? It's the energy required to take away an electron, right? So what we're going to end up with is an ion. What charge will that ion have? Yeah, which one? We've taken an electron away. Positive, good. So we'll have a positively charged ion, and then we'll get an electron. We're coming in on the third page. Next. All right, so that equation right there is important. That's the reaction. If you start with a neutral atom and you supply enough ionization energy, you get a positively charged ion and an electron released. Okay. They go together, they're related. So we talk about electronegativity and electron affinity. So electronegativity and electron affinity, they're closely related. Electronegativity is the tendency of an atom. Well, let me ask you this. When we talked about ionization energy, we were doing what to electrons? Yeah, for ionization energy particularly, it's the energy required to take away an electron. So now we're probably going to talk about gaining electrons. Does that make sense? So electronegativity is a measurement of how likely an atom is to attract an electron. So the higher the electronegativity, the more likely an atom is to steal electrons from other atoms. I always think of it like this. We think of it as like hunger, all right? How like electron hungry is it? Or I like to think of it, if, we're fighting over some electrons, fight with me? Yeah, we're fighting over electrons, it's who's stronger. And of course, obviously that's, okay, so there we go. I'm not very strong. Devin Chiklovsky once was in my grade 10 science class, and he was useless. He didn't do anything. But every day, Orlando, he was like big into like bodybuilding at the time because he's like this big. So anyway, but he was working out quite a bit, and he was like, Orlando, arm wrestle me. And I have no upper body strength. I just like eating. So I'd always say no for, I think, obvious reasons, because I don't want to be embarrassed by a kid like this big in a grade 10 class. And so one day I was like, Devin, stop asking this. I'll make it real simple for you. You get 85 or better on the next unit test. I'll unwrestle you. Thinking like, there's no way. Right? Like I thought that was just the safest bet that there's ever been. Didn't he get 92%? 92% on the unit test. And then we had a mighty arm wrestle and I did not win. But I like to think that I put up a good fight. Anyway, that's electronegativity. It's a measurement of which atoms have a greater pull on electrons. Right? And we can think of it in the same terms, which is that electron affinity is the actual energy we get from gaining an electron. So when we lose an electron, we have to put energy in, right? That's what ionization energy told us. That if I'm going to take an electron away from you, give it here, I have to put energy in, right? Because I'm stealing it. I'm sorry. I don't know my own strength. But if we have to put energy in to steal an electron, when we gain an electron, energy is actually released. When we gain an electron, energy is released. All right, and electron affinity is the measurement of how much energy is released. So see how these are related? Electronegativity tells you how badly it wants to get new electrons. Electron affinity tells you how much energy is released when that actually happens. All right, and again, think of it this way. The orbitals further from the nucleus are less likely to attract electrons, right? If you have a big, huge atom, that valence shell is pretty far from those positively charged protons. And so the pull on electrons is pretty low, right? Whereas if you have a really small atom, its pull on electrons is pretty big, right? So this follows the same trend, all right? Electronegativity decreases as you go down the table, and electron affinity does the same. And then again, electron orbitals, as we move left to right, the orbitals get smaller and smaller. We get closer and closer to the nucleus. There's more and more protons to attract. So if there's a high number of protons in the nucleus, electronegativity and affinity go up. And so the trend is that as we go left to right on the periodic table, these things go up as well. All right? And there's the trend. You'll notice the trend for this is exactly the same as the trend for ionization energy, right? Oh, stop. They don't like me today. Oh, that's not what I wanted either. Okay. Okay, and before, I've got this little section keeping it all straight, but this has an equation as well, right? In this case, we start with an atom. And for electron affinity and electronegativity, it is gaining an electron. So we get an atom, and we add an electron. Once that happens, what do we get as the product? Once it has a charge, we don't call it an atom, we call it an ion. What charge will that ion have? Good. And then what else is released? Energy. All right? And we call that the electron affinity. But just to be clear, that is a measurement of how much energy is released when this happens. Does that make sense? So when we gain an electron, energy is released. When we lose an electron, energy has to go in to make it happen. I have to put energy into a system to take an electron away. But if I give a system an electron, it releases energy. Now, how to keep it straight? It's actually not that bad. If you can remember the trend for radius, all of the other trends go in the opposite direction. That's exactly right. So if you can remember that the radius is backwards to the other three, remember that radius increases as you go down, and it increases going right to left, right? And all of the others are the exact opposite trend. Oh, sorry. All right, and that's it. That's the whole shoot and match. Oh, don't care about that. Okay, did I get your quizzes? Did I not? Where am I here? And